I, um, when I'm solving this part, do we have to do the matrix multiplication for this and then find the then use the matrix table you gave for all the cos and sine, then substitute the theta value from that, or how does it work?
Right. So remember, whenever you have a transformation matrix, it's always between two things, right? And so when we're trying to find the angle between two segments, so what I've given you here are basically two matrices for the upper arm.
Okay.
And so, but you spent the other earlier parts of part for the lower arm. And so what you're looking for basically is this transformation matrix. Right. And so you want to find a transformation matrix that relates the ACS of the upper arm and the ACS of the lower arm. And so based on these two, and then based on the results that you computed in the earlier parts of the problems, you should be able to find this.
Oh.
And then based on that, it's just as you said. So you're basically going to have, it's basically going to be a 3x3, right?
Yeah.
And then you're basically going to be looking at this entry up here, or this, and these two is going to be cosine theta, and these two are going to be sine theta. And so first thing you're going to need to do is you're going to need to multiply matrices to get this. Make sure that, remember when you multiply two transformation matrices and their inner dimensions cancel are the same. And so you can see here that we have lab, and when you take the inverse of this, then lab will go on the bottom right there, right? You multiply them, those two will cancel. And so you're going to perform a lot of multiplications to get this ACS up, ACS lower, or it can be swapped too. So you can have lower on the top and upper on the bottom. It doesn't really matter. And then you're going to take an inverse sine or inverse cosine on the entries to get the angle.
Okay. So I do the inverse of this and make sure I get ACS R lab, and then I forget the ACS the ACS lower part, and then multiply those two.
Exactly.
Okay.
Work it out with the symbols first. And so don't plug in any matrices first, because you have all the symbolic forms for each of these, right?
Yeah.
And so find the right combination of multiplication. You might have to do some inverses too, because remember when you inverse it, you swap the positions of those two. And so work that out first. You should be able to do it within three matrices. So you're going to need to use these two, and then a big hint is that you can do it with either part 1, part 2, or part 3 of this problem. And so you multiply those three together, you get this, and then you perform that multiplication
And get that.
exactly.
Okay.
Exactly.
Thank you.
Yep. Mhm. All right, it's 4 o'clock. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. All right, so we are end of week 12. I'm back, by the way. So, back on campus. Unfortunately, it's cold, but I'm here. All right, and so today, my plan for today is that we're going to finish up everything. So after today, today's kind of the cutoff for the midterm. So, our next midterm is going to be next Thursday. And so my plan is that, by the end of today, that's everything that you're going to need to know for the midterm. And then we'll cover new stuff on Tuesday, but, Tuesday, that's a little bit too short of a notice, before the midterm. And so I like to cut things off kind of a week before, the actual midterm exam. And so we'll finish that up today. We have one more example to do with inverse dynamics. And then we're going to get into kind of the first half of muscle force optimization. And then you only really need to know just the conceptual stuff for that for the exam, but then, we'll see how far we can. Okay. All right, so remember, homework 5 is due on Tuesday. And so I've definitely gotten a lot of questions on it. I did make some mistakes in writing up my solution. So I updated the PDF. So you should have gotten an email about that earlier today. And so if you're working on the homework, especially I think part 4, problem 2, 2A, and then all the moment equations for problem 3, the solutions have been updated. So make sure you take a look if you're not getting the same things. Okay. All right, and so that's it for my announcements. Are there any questions I can answer before we get started for today? Okay, all right, let's go ahead and get started. I remember we were going over inverse dynamics. All right, so remember the idea with inverse dynamics is that, now that we have quantified and we can measure the kinematics of human motion in terms of the body angles, joint angles, the joint angular velocities, angular accelerations, we can then translate that information to compute what are the net forces and moments at the joints. Okay. Because ultimately what we'd want to be able to describe is that, if we observe someone going through a motion, we want to know, how much force is each individual muscle exerting to produce that motion, because, that's useful to know, for a variety of reasons. But, maybe if someone's getting hurt in a particular maneuver, or if someone wants to increase their performance. So it's always helpful to know, which muscles they should work on to, improve certain outcomes. So we're not quite there yet. And so that's kind of the next topic on muscle force optimization, but this is kind of the second step. And so we've done the first step, which is kinematics. We've done the motion capture. We've characterized the kinematics in terms of joint angles, angular velocities, so on and so forth. Now we're determining, what's the net forces and moments that are needed to produce that motion. Okay. And so last time we spent quite a bit of time doing a pretty extensive example. And so today what I want to do was I want to do just one more example of this, just so that you can get another look and see how this is done. And we're going to do a different part of the body on this one. And so, hopefully with this example, combined with the last example, we're going to give you a fuller picture of how this is. So I think that'll maybe take about 30 minutes a day, and then we'll move on to muscle force optimization. Okay. Okay. And so in this example, we're going to look at the inverse dynamics of a dumbbell curl. And so let's go ahead and draw a model here. And so this first dot I'm going to draw up here, this is the shoulder joint. And so from the shoulder joint, we're going to go down. Okay, so we're going to go down that. That is the upper, that segment right there is the upper arm. The segment down here is the lower arm. Okay. So this right here would be the elbow. This right here would be the wrist. Okay. So we're kind of looking at a side profile of the arm. Okay. In the hand, and we're gonna ignore the hand for a second. So we're gonna assume that the weight is being applied at the wrist. Okay. At the hand, we have our external force, and so we'll say that FW here. FW here is the external force from dumbbell. And so that gives us kind of a little bit of a hint, right? Remember, whenever we do an inverse dynamics analysis, we always want to start with the segment where the external force is being applied, okay? So in the previous example, the one we did in class on Tuesday, that was from the ground reaction force. And so we started from the foot. This time it's coming from a dumbbell. And so we're going to start with the lower arm segment because that's where the external force is. And for the homework problem, problem 3, if you haven't started it yet, we're actually going to start from the other side. And so in problem 3 on the homework, we don't have any measurements of the external force. And so any kind of, and so the external force that we're going to use actually is coming from the torso, right? And so you're going to start the analysis from the hip and then kind of work your way down to the foot, right? But in this case, we're going to start at the wrist because that's where the external force is. Okay? Let's go ahead and characterize the centers of masses. And so in the middle of the upper arm, we have our center of mass. And so we have the M2, I2. Okay. And in the lower arm, we have the its center of mass. And so it has a mass of I1, moment of inertia I1. Okay. The distance from the shoulder joint to the center of mass, we'll call this R2. And the total length of the upper arm segment is L2. Okay. We're going to find the same quantities for the lower arm. Okay, so R1, L1. And then the last piece of information that we need are the joint angles. And so remember, the joint angles we always measure relative to the positive x-axis. And so for the upper arm, we're going to go all the way around like that. And so this angle right here, this is theta 2. Okay. And for the lower arm, we're going to go all the way around, starting from the positive x-axis and rotating counterclockwise until we reach the lower arm. And so this is theta 1. All right, unlike the last example, so the last example we just did in terms of symbols, this one I'm going to give you numbers for. And so the numbers for this one, we'll start with the values of the lower arm. We have M1. M1 is equal to 1.37 kilograms. I1 is equal to 0.0084 kilogram meter square. Is 0.13 meters. One is 0.272 meters. Okay. Then we have the same properties for the upper arm segment. So M2, 2.37 kilograms. I2, 0.0175. Kilograms meter square. R2 is 0.151 meters. L2 is 0.298 meters. Okay. Right. In addition to those, all those parameter values, for this one, we're going to assume that we have motion capture data for this. Okay? And so we're going to have values for all of the joint angles, the joint angular velocities, and the joint angular accelerations as well. Okay. And so just to kind of give you an idea, we're not going to plug in every single value of these because it's going to be a little bit too tedious. But this is just to kind of give you a sense of what the data would look like if you were to have the kinematic data. Okay. Right. And so our main kinematic variables here are the joint angle, the joint angular velocity, and the joint angular acceleration for the lower arm. Okay, so theta 1, omega 1, alpha 1. The same quantities for the upper arm. So theta 2, omega 2, alpha 2. Okay. All right, so I'm going to put this in tabular format. And this first column here will be the time values. Okay. And so let's assume that we've measured these over five successive time instances. And so maybe each row here is separated by maybe like 0.1 seconds or something like that. Okay. Okay. And so the joint angles for the lower arm, if we track that as a function of time, it may have the values of 5 pi over 3, 16 pi over 3, 0, pi over 6, then pi over 3. Okay. And all this, of course, is in radians. All right, so for the angular velocities, let's say I start with 100 and 200, 150, 5 and 0. And the units for angular velocity are radians per second. We have the angular acceleration. So 500, 500, minus 250, minus 125, minus 625. And the units for this are radians per second squared. Okay. Quite a bit of numbers here. And so typically these kinds of calculations you would perform it on a computer. And actually, I do have a MATLAB script that computed a lot of these for us. And so the only thing that you would have to do by hand would be to set up the equations, which is what we're going to get practice with. Okay. All right, and so we're going to assume that this person has pretty good form when they're doing the bicep curls, and so we're going to assume the upper arm stays mostly stationary. So the upper arm, we'll say, is locked at a joint angle of 5 pi over 3. And we're going to assume the upper arm is not going to move. So the angular velocity and angular acceleration for the upper arm are all going to be zeros. Okay. All right, so there's a lot going on in this problem. So a lot of numbers. And so let's state our end goal. So our end goal is to compute. Okay. We're going to compute the net joint forces and net moments at the elbow and shoulder joints throughout this dumbbell curl. Okay. All right, any questions on this? Just set up a problem. Okay. All right, so this one, even though there's a lot more numbers here, in terms of the equations, we have a little bit less work to do than the previous one because we only have two body segments here. We just have the upper arm and the lower arm. And so we're going to proceed in the same way that we did before. And so starting with the most external body segment, and so, starting from the segment where we have the external force applied, which here happens to be the most external body segment. And so we're going to draw a free body diagram of that part. We're going to include the internal forces and moments at the joints, and we're going to set up our equations based on the equations of motion. Okay. Okay. So let me go ahead and draw kind of an exploded view or just a bigger view of the lower arm. Okay. And so our lower arm is looking like this. Okay. First, let me draw the angle. And so this is omega 1 or theta 1. We have the center of mass here. So we have M1, I1. Where we have a vertical force M1G, which is the weight, basically the weight of the lower arm, okay, acting at a center of mass. Distance from the elbow to the center of mass is R1, and the length of the entire elbow is L. In terms of forces, we have the force from the dumbbell, and so that's FW, and so that's a weight force pushing downwards. And then we also have the internal forces within the elbow itself. And so at the elbow, we have FEY, and then FEX. Okay. FedEx. Okay, so that's the force, the net force at the elbow in the Y direction, net force at the elbow in the X direction. Okay. And then we have the net torque at the elbow as well, so T. Okay. And so these three quantities right here are unknown. Yeah.
Why did you pick initially next?
Yeah, that's a good question. So, so that's just kind of I like to put for the segment that I'm going on right now. I like to have both the Y and the X direction starting in the negative direction, so that when I move on to the next segments, they're going in the positive direction. So it's really up to you. So you can choose which directions you want for it, as long as you kind of stay consistent with that direction. So when you move on to the next segment, they should be in the opposite directions. Yeah, but you can easily do this going in the opposite directions as well. Yeah. Mm-hmm. Okay. All right, so that's all I think that's all the forces accounted for. Yep. Okay, so let's go ahead and do our equations of motion. All right, so let's do some of the forces in the X direction, sum of the forces in the y direction, and we're going to sum the moments. And remember, the best location to sum the moments around is the center of mass. Otherwise, we have to deal with that kind of extra term in our moment equation that we don't really want to deal with. Okay. All right. So in the x direction, we just have a single force here, and so we have minus FEX. Okay. Right, and that's equal to mass times the acceleration of the elbow segment in the x direction. Okay. Okay. Then we have the sum of the forces in the y direction, and so we have three forces in the y direction. So we have the elbow force there, so that's minus FEY. We have the weight of the arm, so that's minus M1G, and then we have the weight of the dumbbell minus FW, okay. And that's equal to the mass of the lower arm M1. This is M1 times the acceleration of the elbow segment in the y direction. Okay. And then finally we have the sum of the moments around the center of mass, and so we have minus TE. Because that torque, the way we've drawn it, is going in the clockwise direction, so we have a minus there. So we have minus FW times L1 minus R1, because that's the distance between the dumbbell and the center of mass. And it's cosine theta 1 plus FEY R1 cosine theta 1 plus FEX R1 sine of theta 1. Okay. And this is equal to I1 times alpha 1. Right. So these three equations here, these are our equations of motion, okay? And so these are going to give us three equations to solve for our three unknowns, right? So FEX, FEY, and TE are the unknowns that we can solve from this equation. The only issue with these equations is that the acceleration of the elbow joint, or excuse me, of the acceleration of the lower arm with respect to, it's linear accelerations. We have to actually compute these based on the joint kinematics. And so we're gonna do the same thing that we did last time. Okay? Let's just do X. Okay. So just like we did last time, we're going to form expressions for the X coordinate for the center of mass as well as the Y coordinate. Okay. And this is another thing that you kind of have freedom to do as well, because it depends really on where your origin is. Okay. So if you remember from the example we did last time, we chose the foot as kind of our origin because that was kind of the most stationary point. Okay. And then all locations, all velocity accelerations were measured relative to the position of that foot. Okay. For this example here, our most stationary point is actually going to be the shoulder, right? And so we're basically assuming that the shoulder is not moving and the arm is just kind of curling from there. Okay? And so it kind of makes sense to make our shoulder here our origin. Okay. And so all distances and all locations for the lower arm and the upper arm they're going to be measured relative to the shoulder joint. Okay. And so this X and Y here, this is assuming, or I should say relative to the location of the shoulder joint. And so from the shoulder, we have to cross through the upper arm as well as halfway through the lower arm. So we say X E here is L2 cosine theta 2 plus R1 cosine theta 1. Okay. And then YE, actually let's do X first and then we'll do Y. I think I'm gonna need more room. Okay, so let's take the velocity of the lower arm segment by taking the derivative of the previous one. Okay, so we take the derivative of this, we get minus L2 omega 2 sine theta 2 minus R1 omega 1 sine of theta 1 and then we take the derivative of again to get the acceleration. Okay. So I did this kind of quickly, but we went over it kind of in detail last time, where whenever you're taking the time derivative of these positions, make sure you use both the chain rule and the product rule. Make sure you grab all the terms. Okay. And so we have an expression for AEX. And so this is going to plug in straight up here. Okay. And then let's do the same thing for Y. And so we have YE is equal to L2 sine theta 2 plus R1 sine theta 1. Let's take derivatives. L2 omega 2 cosine theta 2 plus R1 omega 1 cosine theta 1. AEY L2 alpha 2 cosine theta 2 minus L2 omega 2 squared sine theta 2 plus R1 alpha 1. Okay. And then you would take this expression here and plug it in for AEY. Okay. All right, any questions on how we did any of this? Okay. All right, I know it's a lot to write down, but if you look at everything in pink right here, these expressions are very, very long, but remember they all contain, they basically are entirely comprised of kinematics data. And so they're all lengths, they're all joint angles, angular velocities, angular accelerations, okay? And sine and cosine, of course. And so what's unique about everything here is that you can actually compute these. And so if you plug in a lot of the data that we had at the beginning of the problem, L2, R1, those are all given to us. If we go back up here, theta 1, omega 1, alpha 1, theta 2, omega 2, alpha 2, These are all given to us. And so you can actually plug into these expressions and get a number from this. Okay? Even though it looks nasty, they end up just being a number because we know everything. Okay. All right, and so you can plug these in. And then after you plug in for AEX, AEY, then FEX, FEY, and TE, all of these you can solve for. Okay? So this set of three of equations right here is actually a closed system. So we have everything that we need to actually solve for. Okay? And so there's only three unknowns, right? So we can take these three equations to solve for those three unknowns. That's not always the case. And so I think what you'll see in the homework problem especially is that you'll form three equations per segment, but each segment individually will have more than three unknowns. And so you wouldn't be able to solve each segment individually, but when you combine all 9 of the equations in total, then you'll have 9 equations for the 9 unknowns, and you can solve them all together, probably most likely with some kind of computer software, because that's a little bit too much to solve for by hand. Okay, any questions on this? All right, so very quickly, let's do the upper arm, because upper arm is kind of more the same. It's just going to be a little bit simpler. Okay. Okay. The upper arm, let's go ahead and draw a bigger version of it. It looks like this. Okay. So remember, up here is the shoulder. Down here is the elbow. Okay. Let's draw the joint. Let's draw the joint forces first, starting at the elbow. And so remember our convention. And so because we took the negative directions for the elbow joint from the lower arm, right? So we said FEY is going down, FEX is going to the left, okay? And TE is going clockwise. We have to choose the opposite directions here for the upper arm. Okay? And so for FEY is going to go upwards, okay? FEX is going to go to the right. And T1 is going to go in a counterclockwise way. Okay. All right, so let's do the same thing for the shoulder joint. So for the shoulder joint, we're not going to go beyond that, and so in the end, it doesn't matter too much. But just to be consistent. So I'll draw FSY going downwards. And FSX going to the left, okay? And then the net joint torque, or the net joint moment at the shoulder is going to go in the clockwise direction, okay? Those are just the directions that we chose. And so, everything is kind of relative to that. Next, we have the center of mass. So we have M2 by 2. Right? The distance from the shoulder to the center of mass here is R2. And the length of the entire upper arm segment is L2. Okay. And of course, we have the gravity force M2G. Okay. So that's going to be going downwards. All right. So let's go ahead and form the equations of motion, right? So just like we did before. So we're going to sum the forces in the x direction We're going to sum up the forces in the y direction, and we're going to sum up the moments around the center of mass. So some of the force in the x direction, we have two of them here. And so we have Fex in the positive direction, and then minus Fsx, and then minus in the negative direction. Okay. That's equal to the mass of the upper arm multiplied by the acceleration of the upper arm in the x direction. Okay. We'll find out the expression for A2x in a minute, but I'll write out the all three equations of motion first. All right, in the y direction, we have three forces. So we have Fey minus Fsy minus M2g is M2A2y. Okay. Right, and then we have the sum of the moments around the center of mass. And so we have TE minus TS. Okay. So that's the net joint moment at the elbow minus the net joint torque at the shoulder. Okay. Okay. Then we have the joints, we have the torques that are, or excuse me, the moments that are coming from the net joint forces at the shoulder. Okay, so Fsy times R2 cosine theta 2 plus Fsx times R2 sine theta 2. Okay. Okay. And then we have the moments that are being contributed by the elbow joint forces. Okay. So it's Fex, Fey. Right. So here are three equations, but just like before, we're not quite done yet. We need to find expressions for A2y and A2x. Okay. All right. So this one would be a little bit simpler because these are a lot closer to the elbow, or excuse me, a lot closer to the shoulder. And so our expressions for the acceleration are not going to be as big. Okay. And so for instance, the x position of the upper arm center of mass is just R2 cosine theta 2. Okay, just one term. Okay, so we can take the derivative to get the velocity. So that's minus R2 omega 2 sine theta 2. We have AX2 is equal to minus R2 alpha 2 sine theta 2 minus R2 omega 2 squared cosine theta 2. And we're going to do the same thing for the y component. So we have y2 is equal to R2 sine theta 2. Take the derivative, we get the velocity. So we get R2 omega 2 sine theta 2. Okay. And you would plug in those corresponding expressions into the equations of motion. Again, so, fairly gnarly expressions, but, but if you just plug everything into MATLAB or plug everything into a computer or a calculator, then you can compute this. Any questions on how we got these equations here? Okay. All right, so now that we have our 6 equations, we can use them to solve for our 6 unknowns, okay? Because we have every single parameter that we can plug in for. It's just kind of a matter of busy work. And so, I'm going to, I don't think I've posted yet, but I'll post the MATLAB code that I use to compute these. Okay. Because that's all it is at this point. It's just a bunch of plugging in. And so you could definitely do this by hand. It's just a little bit tedious just because there's so much to plug in. Okay. And so what we can get is we can get time histories for all of the net joint forces and net joint moments at the elbow and shoulder. Okay. So we can get FEX, FEY, TE, FSX, FSY, and TS. Okay. Okay. And we can get their values at the 5 time points that we've measured the kinematics at. Okay, so time 1, time 2, all the way to time 5. Okay. All right, and so if we plug in all the values for these, for FEX, we get the following values. And so we get 813.38 newtons. At time 1, at time 2, we get 5,400 newtons. At 3, we get 4,007 newtons. And then all the way down to minus 96.4. Okay. And so earlier today, there was a question of, what if you chose the different directions for the, for the joint reaction forces? All that would change for your solution here is it would change the sign. And so, when we started at the lower arm, we chose negative directions for the elbow X force and the negative direction for the elbow Y force. And so if you had chosen the positive directions for these, it would just change these to positive instead of negative. And so, you'd get the same magnitude, it's just the direction would be opposite. Okay. Assuming that you were consistent in making them the opposite direction on the adjacent segment. Okay, so that's FEY. And so most of these are negative. That means the true direction for the elbow reaction is in the other direction. Okay. We have TE at minus 208.6 meters. I just squeeze it in a little bit because the units for moments are newtons meters. Okay. All right, so that's everything for the elbow. So that's the joint reaction forces, the net forces at the elbow joint in the X and Y direction, as well as the moments. Okay. Now we have the results at the shoulder. Okay. And if you remember, the upper arm was stationary throughout this whole time, right? So we assumed that the upper arm stayed completely still throughout the motion. Okay? Even so, the forces that the upper arm is going to experience are still going to be relevant. Okay. So those are the X and Y forces at the shoulder joint. Okay. And then we have the torques. Right, so that's what you get for all the plugging. Okay, so it is once you kind of start to get the numbers into it, it is quite tedious because there's a lot to do. So normally this part here is done with the computer, especially once you actually get some real motion capture data, you'll see that it's way too much data to actually process by hand. So the importance of them for the last I would say 4 weeks, we've been going over all of these methods. Really, a lot of these methods are kind of designed for computers to do. And so, what you are kind of responsible for as an engineer is to, first of all, understand, how these methods work, but also just understand how or where the equations come from. So you can kind of set it up yourself. But the actual kind of, nitty gritty, doing all the calculations, that's actually done by a computer just because it's kind of way too much for a person normally to handle on their own. Any questions on this before we move on to the next topic? Okay. All right. And so the last thing that we'll go over in kind of this section. Oh, was there a question from Zoom? I'm just hearing things. I'm going crazy. All right. So the last topic that we'll go over in kind of this section of human dynamics is what I call muscle force optimization. And it's kind of the last piece of the puzzle that we need in order to kind of fully realize our human dynamics analysis. All right. Okay. So muscle force optimization. So what does this mean? And so, let's kind of take a step back and look at our journey that we've taken to get here so far. So we've done, we reviewed muscles, right? So we kind of remember what muscles did. We did inverse kinematics. And so we took basically motion capture data and we used that to describe the motion in a certain way. Okay. Then from kinematics, we went to dynamics. Right? So that's what we just finished. And so, what we get from dynamics is that in order to produce the motion, we have to have certain net forces at our joints. Okay. The next step is to take that dynamic information, take the joint information, and then translate that into muscle forces. And so we're basically asking the question is, what is each individual force contributing to the net joint forces and moments at the joints? Okay? because that was kind of our ultimate goal, right? And so if we observe someone doing a motion, either doing something like maybe an exercise like a push-up or something like that, we wanted to know, based on what we can observe from that person, how much force or how much work is each individual muscle doing to produce that motion. Okay, and we're just about ready to do. Okay. The problem is, this part right here is very, very complicated. And it's complicated for a number of reasons. And so probably the number one reason why it's complicated is because there's a lot of built-in redundancy in the human body. Okay. Okay. And what I mean by that is that if you wanted to produce a certain motion or produce a certain amount of moment around a joint, there are often multiple muscles that can produce that moment or produce that force. Okay. Sometimes it's like 3, sometimes it's 4, sometimes it's 5. And so, there's kind of more than one muscle that can contribute to a particular motion. Okay? And so it's when you observe basically what I mean by that is when you observe a motion from the outside, you can't say definitively that that's, this muscle is contributing this much of that just from outside observations, because it's different for everybody. Okay? And in general, redundancy is a good thing, right? And so you don't want certain particular actions to depend on just a single muscle, right? Because if it just so happens that muscle goes down, either it gets hurt, okay? You don't want that to kind of eliminate a total range of motions that you can do, right? Also, it's good just from an energy standpoint too. And so when you have a motion that only one muscle can contribute, you're going to tire out that muscle very quickly over a few motions. So the fact that you have multiple muscles with each of their own kind of ecosystem of musculature, backing it up, it really helps in kind of stabilizing and kind of helping with any kind of issues that may come up. Okay? But at the same time, each of these different muscles has its own unique geometry and has its own unique characteristics. Okay? And so by geometry, of course, I mean things like the size, the length, but also things like its moment arm and attachment angle as well. Okay. And so let me bring up an example. We actually kind of went over this briefly when we were doing our biostatics, right? And so if we consider the simple action of just flexing at the elbow, right? So actually just almost identical to the example we just did. Okay, so here's our elbow joint. Right, so inside our arm here, we have several muscles that can contribute to elbow flexion. Right? And so the one I think that most people know, we have the biceps brachii. But then we also have other muscles inside there too. And so remember, we have this one is the brachialis. And then we also have the brachioradialis. And so brachioradialis looks something like this. Yep. Right. And so because of the way all three of these muscles attach and kind of where they're positioned in the body, all three of them can actually contribute to flexion at the elbow. Okay. And so when you observe someone, doing a dumbbell curl or kind of lift or flexing at their elbow, it's not just one muscle that's acting on its own. It's all three of these acting together. Okay. And so if you remember, when we did biostatics, we looked at this exact problem. And so the way that we kind of dealt with it then was we made an assumption. And so what we assumed was that the amount of force that the muscle could output was proportional to its cross-sectional area. Okay. Okay. And we kind of use that information to give us some additional equations to solve this problem. Okay. And if you remember back then, I said, I promise you we would revisit this problem because there's kind of a lot more to it than just simply measuring the cross-sectional area. Okay. And so this is kind of where we are. And so that assumption there is not bad. And so we'll still kind of rely on that a little bit here. But like I mentioned before, it goes kind of a lot deeper than this. Okay. What's really happening underneath, I guess underneath your skin here is that, remember your muscles are controlled by your central nervous system. And so your central nervous system is going to be the one that's going to tell how much force each muscle here is going to contribute. But the central nervous system knows that some muscles are able to exert more force than others, just because of their size, right? But you have to ask, is that the only criteria that the central nervous system is using? Okay, because your nervous system is very smart, and it does a lot more than you kind of think it does. Because yes, it's taking those factors into account, but it's also taking a lot of factors into account at the same time. Because remember when we talked about walking and running, generally speaking, when your body undergoes a motion, it's preferable most of the time to do it in an energy efficient kind of way. Okay. And so when your central nervous system tells your muscles to activate to perform an action, energy conservation is also kind of one thing that is considering as well. Okay. And so I'm going to abbreviate central nervous system as CNS. Okay. And so, like I just mentioned, your central nervous system, think of the central nervous system as kind of like a manager at a job, right? And so they're trying to think about, what's the best way. I have this kind of task that I need to do. I need to flex my elbow because, because we want to. And so they're trying to determine, what's the best way to split the work. And so on the one hand, you have muscles of different sizes, and so you can split the work. That's one consideration that you can use, that some muscles are able to exert more force than others, but there's other factors that they need to consider as well. Okay. So one factor, of course, is energy efficiency. And so it wants to perform the action, using the least amount of energy possible. Okay. Another factor that it may consider is, maybe you're in a life or death situation, right? So maybe someone's, holding a gun to your head and it's like, give me 10 reps of this dumbbell, otherwise I'm going to shoot you in the head. And so maybe you're trying to do it as fast as possible, right? Okay. And so sometimes, energy efficiency is not the most optimal, or it's not the criteria. And so sometimes you want to do this for performance or for speed. Okay? If you're playing a sport, that's generally what you're going to do. And so, let's say you're playing, basketball or soccer or something, and and you have to make a play, right? You're not in that moment. You're not really worried about energy efficiency. You just want to make sure that you can make the play, whatever you need to do. Okay. Or if you're doing like animal locomotion, right? I know a lot of you are working on that for your final projects, right? If you're working on like a prey animal, like a bunny or something like that, sometimes they're being chased by a predator, and so their nervous system is telling them, we need to like haul ass and get out of here, otherwise that wolf is going to eat us. And so in those situations, you're not thinking about energy efficiency. You're just trying to move as fast as you can. Okay, and so it's a very dynamic thing, and so every situation is different. And so depending on the situation, your central nervous system may tell certain muscles to act in a certain way. Okay. All right. And so this kind of begs the question. So very quickly we've gotten to a very complex situation where we want to determine how much force each muscle is exerting in a given motion. But there's a ton of things that we have to consider. We have to consider, first of all, the performance of each muscle, the size. We didn't even talk about fast twitch, slow twitch. So some muscles are fast twitch and slow twitch. Okay. And then depending on the situation, maybe we want energy conservation, maybe we want performance, it really depends. Okay. And so we need kind of a framework, or we need a way to kind of account for all of these things together at once. And so the way that we can do that mathematically is to use something called an optimization algorithm, optimization technique. Okay. So optimization is it's a very interesting subject. I think it's almost like a buzzword. I think people kind of throw around. So they want to optimize this, optimize that, find the optimal this. But when you talk about optimization in a mathematical sense, you're actually talking about something very specific. And so optimization is kind of a very broad class of algorithms, a very broad class of mathematical techniques that aim to find kind of the best solution to a very complex problem, a problem that is kind of too complex to solve with just simple equations. Okay. And so this question or this problem of determining the muscle forces, it kind of falls almost perfectly into the kinds of problems that optimization can do. Okay. Because usually when you think of like an engineering problem, you think about an analysis problem, you think about having an equation or multiple equations and then solving those equations for the solution. Okay. The kinds of problems that optimization are dealing with are ones that they either don't have an equation to solve for it directly, or there's too many equations to solve for at the same time. Okay. And so there's a lot of kind of practical problems in life that kind of fall within that category. Okay. Okay. And so some examples of optimization used in engineering practice are problems that sound super practical, right, or super, super relevant. Okay. So one example, from aerospace, let's say that you're trying to find the optimal shape or the optimal dimension of an airfoil to minimize drag on an airplane. Okay. And so, if you're given a shape, yes, there is an equation that you can use to compute drag. But, when you're talking about an airfoil, which is a very, fairly complex shape, it depends a lot on, a lot on the fluid mechanics. And so it's a very complicated question that most time you have to run a simulation to really understand. Okay. And so to find like the actual optimal shape, size, length, width, curvature and everything like that, that's a little bit too many variables to decide with just kind of one equation. And so a lot of times we turn to optimization to kind of solve something like this. Okay. Okay. Another example that is not so much an engineering flavor. It's let's say that you're interior decorating your home, right? And so you want to find out what's the most optimal placement of the furniture, like the couch, the chairs, TV, all that stuff, to maximize the airflow throughout the room. Okay? So again, this is kind of a more complicated situation where there's not just one or two equations that you can use to solve for it. It's very complex, and I would argue that there's probably multiple answers to this too. Okay? And so this is kind of the perfect kind of problem that optimization can solve as well. All right, I'll do one more. Okay. So let's say that you work for a restaurant, right? And so you want to find out what are the best items to include on your menu and what to price them at in order to maximize sales and that stuff. Okay. And so again, not a straightforward problem that has like a simple algebraic equation that'll tell you, you should put pizza on the menu, right? And you should price it at $10. Okay? And so it's something that's more complex than that. And so this is something that optimization is kind of built to do. Okay. Right. So the thing that all these have in common is that there's no explicit So there's no explicit mathematical formula. There's no magic conjure or anything like that that's going to tell you these. And so this is kind of what optimization is built to do. Okay. All right, any questions on this? Okay. And so I will say, you know, we only have 3 more minutes, and so I don't think I can get to move on to the next part. And so I will say that optimization is a very, very broad subject. And so we're only going to barely scratch the surface here in terms of, you know, how you set one up and how it's used. Okay. But the actual details of the algorithms, you're going to have to take, you know, probably a full class on them. And we actually might offer a technical elective in it next semester. We're kind of still in the process of it, of determining that. And so I know a lot of people are asking questions about technical electives next semester. We might add one on optimization. And so, you know, we're still kind of trying to see. Okay. But, you know, basically, you know, doing an optimization problem is interesting because I think, you know, as an engineering student, I think what you're most used to doing is solving a problem to get answers. Right? With optimization, you're not actually going to be solving the problem yourself. Like a computer is actually going to be doing it for you. But what you need to do is you need to set up the problem. You need to formulate it in a certain way that's going to work with an optimization algorithm. Okay, so when we come back on Tuesday, I'm going to show you exactly, you know, how to actually set up an optimization problem, what to actually look for, what to set up, and then how we're going to pass that on to a computer to kind of do a lot of the heavy lifting for us. Okay, so actually very similar to how we did our dynamics example. You know, we set up the equations for it and we let the computer solve it. It's just that with optimization, it's kind of another level of that, and so it's actually a lot more hands-off than before. But there's almost a little bit of an art to setting up optimization problems that you'll see on Tuesday. All right, so that's all I got for today, and so thank you guys for coming. With what we covered for this one, you should be able to answer the last 2 conceptual questions. So I think it's 1D and 1E on the homework, and so you have basically everything you need to do for the homework. So definitely feel free to finish that. If you have any questions on the homework, you know, I'll be available by email because I know my next office hours isn't until Monday. And so if you have questions, go ahead and email me. I'll be happy to look at your work and to answer your questions. But I hope you guys have a great weekend, and I will see you on Tuesday.
My class this morning says tomorrow is Veterans Day, so you may see less people today.
Oh yeah. I know probably people went out for the weekend. Yeah.
I'm in the group with Austin, and we're the ones who are thinking of doing
Yeah.
a contest.
Yeah.
Are you recommending that we do something different? Or
I guess I just don't know. So what's the whole concept of the competition? Just
yes,
hold it as long as you
like
can?
our town professors just hold the stein as long as we can. So we
Okay.
were gonna like run iterations of like changing body position to try to like reduce the amount of force you have to exert.
Okay.
But kind of like rereading the prompt, it's not really the best idea, right?
So my main concerns was that you know, first of all, how many biomechanical analyses you can get out of it. So I think there's one you can do, I think, with elbow angle. I think there's another you can do maybe with the posture of your back, maybe the lower body. And so I don't know if you can get five unique analyses out of that.
Okay.
And then the other concern I had too was that part of it is also you kind of had to look for scientific articles.
Right.
And so I don't know. I mean, I've never looked, so I don't know. So I don't know I don't know if there's any out there. Maybe you can find something related to it, like maybe like endurance of like, you know, a muscle, something.
Yeah,
like
that's something we're thinking about too.
Okay.
Like the arm raise.
Okay. So I'm not opposed to it. I'm just you know,
hesitant on,
Yeah, so I'm just a little bit worried that
Yeah.
there's enough content there for you to actually do the whole.
Okay.
Because I don't want you guys to just work on it over the next couple of weeks and say like, oh, we've only thought of 3 analyses and we're kind of stuck now.
Yeah.
And so that's my only concern, so.
okay,
But I mean, if you guys have a plan, that's why I asked Austin to like, just, if you guys can talk to me a bit more about kind of what your plan was for the 5 analyses, then you know, I'd be more. comfortable.
Okay.
So, yeah, you don't have to answer me. I mean, if you want to talk about it and then send me an email over the weekend or something, then
Definitely.
then we can talk about it.
yeah, we can just stop on. Thank you.
Yep.
I am not used to this darkness this early.
Yeah, I know, right?